You're wearing a sweatshirt, and I think you're wearing a jacket over a sweatshirt. I don't care what the jacket is. I mean, yeah, it's like no one.
I don't know how people understand. Like, I can't do it.
Judging your candleness.
You know what? You like markers?
I do.
Sorry. How long did you? It was pretty awful. I was scared for you.
Solid, less than a foot.
What would we do without her?
That's a very interesting class.
Is it?
This looks like about 7, 8.
I wish it was kids. That would be an interesting class.
Miss Twist had a teaching talk during first period in Mr. Fang or PJ or whatever we call it. Like someone was applying for the job, so was doing a Zoom lesson. So she was there watching, and she told me that I could take her class and try to teach it, but that I shouldn't like prepare it all. I should just wing it. That the notes would be in the classroom. So you walk in and there's notes, and it's something I have never in my life done. And so it was like a freak show, and the kids just heckle me. But not these kids. But like Alex Lowe was like, if you were our teacher, we'd still be in chapter 6. I'm like, nope.
I asked her if she got her doctorate.
Wait, what?
Shea Boyle.
No.
Shit.
It's about an 8 inches.
Wait, that's like really not that impressive math.
What's going on?
It's done in jest, right? Like
Teaching, she used to substitute in this class and teach up fiction numbers on the board, and they were all like,
product moment correlation coefficient is where we started.
What is that?
I don't even
The
know.
PMCC.
I don't know what that
product, yeah. Still don't know what it is. And then
Well, let me tell you, we use RRO depending on the circumstances.
product placement correlation.
Product placement. What is that?
I don't know what that is.
I place some products.
So today we talk about lipids. Everybody likes lipids.
You know what's good when a baby has a lot of Really? I think when it's large.
Wait, Shea Boy?
It was just joke and you see me behind words.
Which Shea?
Big boy.
It's not even spelled right. P-O-I-F.
Okay, here we are in section 3. Lipids. Got 45 text messages since 8 o'clock. Hope none of them are important. Here are your understandings. Fats are more reduced than carbohydrates and so yield more energy when oxidized. So let us take a minute and think about that. The easiest way to think about that is what Brecken's already doing. He's looking at table 34 in your data booklet. So in table 34 of your data booklet, you'll see a delightful list of the fatty acids that you need to know about. My favorite fatty acid is stearic acid.
I love that you have a favorite fatty acid.
Huh? You know.
I can spell it and I can draw it. Those are the, that's the bar. So stearic acid is the compound, again, table 34. first statement says fats are more reduced than carbohydrates and so yield more energy when oxidized, and that doesn't seem like a really obvious statement to me, but I thought maybe we could do like a little comparison. So there are 18 carbons in stearic acid. You'll notice that there are 18 carbons in most of the acids that are listed in table 34. Seems to be like a special number. And so if I took 3 glucoses, that would be the same 18 carbons. So I'm trying to make the comparison fair by keeping the number of carbons constant. And what I want to do is I want to oxidize both of these because this speaks to oxidation and reduction, so that's what I have in mind. And that means I want my body to be able to burn, sugar and fat. And when my body burns those things, it's going to make carbon dioxide and water. And if we were to balance this, it might take your help. I'm going to get 18 CO2s in each case. For waters, I have 36, so 18. I have 36, so 18. 18 times 2 is 36, plus 18 more is 54, minus 2, 52, divided by 2, 26. And then try that game again. 18 times 3 is still 54, 54, but this time I have to subtract 18 from it to get 36. Hot day. Yes, I believe I balanced those equations. You guys would have just told me to multiply the equation I knew by 3, so I didn't have to work so hard for the second one, sorry. Clearly didn't do this yesterday. So I claim I know which one of these will release more energy. Because it is, quote, more reduced. The fat, I can see it's more reduced because I can oxidize it a whole lot more. Instead of oxidizing it by 18 units, I can oxidize it by 26 units. So if I have to demonstrate this understanding on an exam, this is the kind of thing I might consider writing down. I can oxidize it more. Now Amarachi's like, that's a little bit extra. Why can't you just say that there are more oxygens already in the carbohydrate? So here there's like a 1-to-1 ratio of carbons to oxygens, and here it's not close to that. And so it's clear that there are more oxygens, or it is more oxidized as a sugar, it being carbon, than as a fatty acid. So maybe that would be another reasonable way of trying to convey this idea. Maybe you want to look at the ratio of carbon to oxygen, or balanced chemical equation. When we talk about food, we often talk about counting calories, and so there are some numbers some of you can pull out of your heads. Do you know how much food is in 1 gram of carbohydrate? 4 calories?
9 is the.
And 9 is the other number, yep. And so if you wanted another piece of evidence that you kind of know this, maybe you could just talk about the energy in food, and we associate that fats have a calorie density that's a little over twice as high as carbohydrates.
I feel like I read somewhere that calorie fraction. It's like super outdated.
Yes, because your body cares what it burns, and it's a fight at our house sometimes. If you want to read more, you can read Robert Lustig. He's a guy at Berkeley who talks about sugar and how sugar is just fundamentally different as a food than the calories might suggest.
We're not just lighting our stuff on fire inside our bodies.
And even the 2000 caloric daily intake thing by the FDA isn't generalizable. Obviously it's gonna vary per person.
Yeah.
Some people need more than 2,000, people need less than 2,000. And then even foods themselves, each person receives them differently, your metabolism and other subgenetics also.
Yes, I think it's very
Counting calories, it can be useful for some people, but not for others.
So we have a new class in the department next year that's called Research Methods in Medicine. That's supposed to be like a riff on research methods that y'all take in the IB diploma program. And my dream is actually to look at food literature and talk about what does it take to accept what they're writing about, or how much data have they provided, or where are some things they're telling you and not telling you, and so to use that as what does research look like in a quasi-medical field. So I like this conversation. This is what I want this semester of. Triglycerides, we're gonna try to draw some, look at the ester links. We'll talk about saturated, unsaturated, we'll divide that into mono and polyunsaturated. I didn't have to draw a phospholipid yesterday, which was like a bit of a boon, but maybe I'm ready today to try to draw a phospholipid, we'll see. We'll talk about hydrolyzing these things, easy. We'll talk about steroids, but not today. And we'll talk about how lipids serve as, these are the things it gives me as the list. So I realized it gave me the list, but I have my list over here. So it says lipids act as structural components of cell membranes in energy storage, thermal and electrical insulation, transport of lipid-soluble vitamins. I don't have that. But like, it doesn't mean transport the same way it meant for proteins with them channels going into and out of your cell. It means if you're a bunny rabbit, you can eat all the carrots you want because you'll never get vitamin A poisoning because you don't ingest any fat. But, you know, if you yourself are taking huge amounts of vitamin D, it will store in your body forever. And so if you were to lose weight, you can give yourself vitamin poisoning. So if you can take all the vitamin C you want, right? You just keep taking it in and you will excrete it. Make expensive urine. Vitamin B, they have like the RDA. I don't know that we believe in the RDA, but like the pills for B vitamins are now at like 1,000 or 2,000% or 10,000% of the recommended daily allowance, and that's just because you excrete it. So who cares? Like you are super saturated in B12, go. But for A, D, E, and K, you will actually store it in your fat. And you'll store it for a long time. And it may not be bad to store it because it's like encapsulated, but if you release it, say something terrible befalls you and you're in the hospital and you're laying in bed just eating your body, as some people do in the hospital, you can release all of that vitamin and it can cause like real problems. It seems like a House episode in the making, right? I'm sure we can find the right medical show that happened to watch this go down.
Those are like the more important vitamins, right? Like A is protection, E is like hair and skin, A is body, E goes, what was the other one?
A, D, E, and K.
Okay, yeah.
And the things we gotta be able to do is write down some structural formulas for the making and breaking of phospholipids and triglycerides. Look at fats and think about their melting points or their structures in general. Ooh, talk about how fats go bad. We have two related pathways toward rancidity. Apply the concept of iodine number. We'll do that today because it's fun. We've already talked about energy storage a little bit. And then we'll talk about HDL and LDL as promised in a recent math class. Lipids are the most disorganized class we have, and that's because all they have in common is that they're nonpolar or water insoluble. So it's not a structural feature that groups them, it's just, it's not a common structural motif that groups them, it's the feature that they are hydrophobic that groups them. I don't care where you get your list of things that they allow you to do. I was trying to come up with something I could remember. And so my list is here. We already talked about it. Their list is there. It doesn't matter. It's not going to be a list everything they do. It's going to be a list three things that lipids do for you. And I think most of us would get to stored energy. I think a lot of us would get to membranes. And then insulation and protection seem pretty intuitive. You imagine like, all of your organs have like a little fat insulation to keep them all safe as you jostle your body around. You might also think about that other class of lipids, steroids. They're hydrophobic, and so testosterone, estrogen are going to fall into this category. And as soon as you say those words to yourself, you're going to think hormones. So while insulin is also a hormone, it's a huge class of compounds. This is probably what you think of when you use the word hormone. I gave you a table of fatty acids because this is essentially unreadable. 4 in your name. What they have in common is a Q at one end. They all have an even number of carbons. I don't know why it is. The shortest ones have about 4. Butyric acid smells like vomit. Yes, there was some clown who wanted to use it for their IA, and I kept saying no. I do not need that in my life, right? You would call it butanoic acid if you named it right, but that's how we call it in like American street slang, butyric acid. And it goes all the way up here. I believe that myristic acid, which is a saturated chain of 14 carbons, is the fat that's in coconut. So we'll talk about coconut a little bit, because some of you know a little bit. Oh look, it says all of this. There doesn't seem to be really an upper limit on how many carbons it can have. Some plants make 28. I'm sure we can draw a normal distribution and look at a sample. We're going to be interested in a few vocabulary terms. Saturated versus unsaturated is going to tell us whether we have only single bonds, or perhaps if we have at least one double bond. Mono means exactly one double bond, while poly means more than one double bond. That seems painfully intuitive. If you look at your list of fatty acids in table 34, and you check out my bestie stearic acid, which category does it fall into? It's saturated fat with 18 carbons. You can see that here. You might remember IHD if you really want to, go overboard, and you can convince yourself that there are no double bonds there. But you can also see how they drew the fatty acids, and you might check out oleic acid. Oleic acid also has 18 carbons in it. Again, it seems to be a bit of a sweet spot, but I don't have a reason for that. And oleic acid with its singular double bond would be a mono unsaturated fat. That's what you find in mostly olive oil. Whereas if you went down to linolenic acid, it's a polyunsaturated fat with 3 double bonds. On top, I'm showing you a saturated fatty acid that has, only single bonds. On the bottom, I'm showing you a polyunsaturated fatty acid with its 3 double bonds. Some of you are familiar with omega-3, omega-6. The idea is that carbon number 1 is the Q carbon. But if fatty acids can be anywhere from 4 to 28 carbons long, we find that your body doesn't really treat them in terms of their length always. Sometimes it treats them in terms of the placement of those double bonds. That's like how they move around your body, how they are transported. And so in the spirit of Greekness, we decide that the first letter of the Greek alphabet is alpha, and the last letter of the Greek alphabet is omega. So I'm not really bothered if this is carbon number 10, carbon number 20, or 24. I'm just going to say, yo, everybody, check out the other side. And in the instance of an unsaturated fatty acid, I'm going to count carbons, 1, 2, 3, and I would call this an omega-3 fatty acid. Now you guys are going to say that there are more double bonds than that. This is in fact an omega-3, 6, 9 fatty acid. So my claim is that if you took some sort of a homologous series of this linolenic acid and put a whole bunch more methyl groups, where I have circled the singular methylene group, it would still behave in a similar way in some of the pathways in your body, a way I don't pretend to understand. I don't know much about this. Where would I find an omega-3 fatty acid? Fish oil. Where would I find an omega-6 fatty acid? I think omega-6 implies there's not an omega-3. So it's implying there is no double bond there. I think we find it in maybe peanut butter, maybe nuts and seeds are omega-6s. I think that generally we believe omega-3s are good for heart health, and we're not really super confident about omega-6s. We think they may not be super good for you. But mostly when we talk about things that aren't good for you, we're not talking about saturated and unsaturated fats the way we used to. We no longer believe that unsaturated fats are somehow superior to saturated fats, but we do believe that there is a distinction between cis and trans that's really important. Now this isn't much of a 3D-ish picture, but you can sort of see some things. You can see that they tried to make around this double bond, the hydrogen and the hydrogen occupy as much as they could different sides of the double bond. Remember, there's a barrier to rotation here, and they are trying to draw this in the trans conformation. To me, what we find is that naturally all fats exist in the cis conformation. Again, a fat has a coup at one end, and a saturated fat has this beautiful pattern. I'll put carbons in it, I don't know. It looks to me like a zipper. I don't know how it looks to you guys. But all of these have two hydrogens coming off, and we can dot and wedge them if we want. Is that adequate? Like low energy, but adequate. My understanding is that if I put two of these fats next to each other and just showed you the backbone like any self-respecting organic chemist might do, you would start to draw something that kind of worked like that, where they actually can almost fit into each other. They have almost a complementary shape, and so even though there's free rotation, they can like maximize their interaction. And when we maximize an interaction, when we get as close as we possibly can, we are maximizing the London dispersion forces between these two things.
This virus closed yesterday for coronavirus.
Excellent.
Gandhi was asking because we thought it's over everything, so we thought it was gonna do like a trans fat or question. That comes up every now and then, and she explained that trans because it have enough bends, they can kind of snap onto each other, so they act like a solid in your arteries and stuff. But the other one, it doesn't.
It kinks.
So it can't get like a solid. That makes sense.
Yes. Apparently going to do exactly what she did yesterday, so I'm just going to keep going. So we maximize our London dispersion forces, and whether we have these 3 fatty acids or whether we grew this into a triglyceride, it wouldn't matter. We would still say that they can get close packing, strong London dispersion forces. And when we have strong London dispersion forces, we associate that with a higher melting point. So saturated fats are what you find in animal products. So if you imagine the marbling in a steak, it is a solid. If you imagine the stick of butter, it is a solid. And it's because of this close approach due to the close packing. Now if we unsaturate this, instead of having those pretty single bonds, we're going to have a double bond. So I'm still going to have a coup at one end. But right here, I'm actually going to make a cis. That angle looks bad. Whatever. Linkage. When I make that cis linkage, when I make that hook or that kink in the structure, it's not possible for the next one to come and pack the way it used to be. This one is going to have to turn even earlier, perhaps, and that is going to mean that we have to be farther apart on average. Because we're farther apart, the strength of our interaction is much weaker, and as Amarachi already told you, what we find is that these are typically liquids at room temperature, so they're farther apart. They have weaker London dispersion forces. They have lower melting points. They're liquids at room temperature. On the right, I have what we typically refer to as a fat. On the left, I have what we typically refer to as an oil. The distinction in English is fats are solids and oils are liquids at room temperature. There is no structural difference.
Wait, but you said that one is cis, but the other one is trans.
That's correct. Now it ends up that animal products are really expensive. Somehow I was trying to grow a cow in the other class. And can you imagine how expensive it is to raise a cow? They eat a lot. I grew up in a world where they were trying to use cheaper oils, but make them behave like delicious butter. So if you've ever had French pastry, you know that lamination in the croissant is the bomb, right? So you need it to be a solid when it goes into the oven so that it can vaporize some water and separate the layers and be extra delicious. And so Parquet's like, yo, I can do that for you. What I'm gonna do is I'm gonna put a catalyst into this cheap corn oil, and I am going to make this double bond flip from cis, naturally occurring, to trans. And now, like those of you who are angry at the world are gonna tell me that those two bond angles are 120 degrees, not 109.5 like they were in the saturated fat. So there's like a little bit of a blip here, but what we find is that if you turn that corn oil in the margarine, it packs just about as well as butter. And so we had commercials on TV about how margarine was the new hotness, how you could make delicious baked goods with it, how it was gonna revolutionize the world. Unfortunately, your body doesn't process this well. This has been linked to a lot of metabolic disease. Trans fats have been removed from pretty much every product that they used to be in, but like Ritz crackers used to taste better, Oreo cookies used to taste better. This is the magic of delicious. Just the crunchiness was better. Okay, that was a good talk. Just like you have to ingest some amino acids, you also have essential fatty acids that you have to eat. You are not able to make in your body. Linoleic and linolenic acids are apparently examples of these, I think, based on this. I don't know. They also have that omega-6 look. What does that mean? And so here's my list of omega-3 fatty acids. Let's see how we did. Plant seeds, vegetable oils are omega-6, fish, shellfish, and flaxseed oil are omega-3. So that's why I thought my peanuts were probably omega-6. I love Jif crunchy peanut butter. There was like a shortage in Houston not that long ago. Dude, there was no Jif peanut butter in the store.
It's because it was all recalled. It was like
Yes.
poisoning my dogs.
Yeah,
They
maybe
love
that's
their
why.
peanut
But I like Jif peanut butter and it was all gone.
butter. We're trying to
Like you have recalled peanut butter?
No.
Okay.
Because we were trying to finish how much capsule we're providing it. We're like finishing it, we're never not to have a loss out of it. And we're going to buy liters now.
You gonna buy natural peanut butter?
Natural peanut butter? That's a honey.
Like I understand it's better, but
It just tastes worse.
I thought it was
At this point in our lives, we are proteins.
I feel like if they could homogenize it, maybe I could tolerate it.
Yes, because seeing the layers separate makes me want to die.
I-
like churn it before I like.
Right? And it's way harder. And when I want peanut butter on my toast for breakfast, I'm not interested in a project. I'm interested in breakfast.
And they'll say no stir, and then you open it and you have to stir, like you're scaring
Okay,
everyone.
so it's back in the, like, so I ran out and the store was out of it again, and we haven't recalled it for poison, like they just didn't have it. So I finally got it on Sunday. It's been a really good week of delicious toast with peanut butter for breakfast, except for today. Apparently, a lack of fatty acids leads to depression.
Oh.
So please take care of yourselves and find something in this list that you like. And you know, ingest a little bit to help yourselves a little.
Maybe that'll help.
I eat a lot of fish, but I'm still depressed.
I'm not saying it's a cure-all. I'm just saying like it could help. It also helps your skin. So in nature, we normally find the fatty acids by themselves. We find them wrapped up in triglycerides. To make a triglyceride, we take the beautiful molecule 1,2,3-propane triol. Or as your evil book wants to call it, propane 1,2,3 triol. Sorry, I'm never going to get there. It's a triol because, you know, it's got 3 alcohols on it, 1 at each position in the propane, thus the 1, 2, 3. There he is, looking all cute. And a unit of fatty acid comes up to that. And a reaction ensues. It is thought of as a condensation reaction because it's going to make 1 unit of water, but also an ester linkage. I'm not going to do this one time. Problem for later. Problem for later. I'm not going to do this one time. How many times am I going to do it, friends?
3.
And I'm going to make myself a triglyceride. So again, that marbling in the steak or that deliciousness in the butter is actually associated with this deliciousness. Yeah, you're bored. I'm sorry. I'll try harder. Like I need pluses somewhere. Easy peasy. So I think a difference, and tell me that I'm wrong, between this class and another class that some of you take is that you legitimately would have a 2-mark question that's like, draw this. And so they'll say, Emma makes a triglyceride with 2 units of stearic acid and 1 unit of linolenic acid. Draw the triglyceride. And so you got to throw down this, you got to throw down the 3 fatty acids from your data booklet, you got to make the yield 0, the 3 waters, and the 3 fats have to be there. What? No, in this class, like I think a difference is that I expect you to be able to draw this structure. I don't think it's a hard problem because I think it's one that you all understand, but it is an art problem. So like he's doing his homework that's due today because, you know, kind of good, kind of bad. And if you actually did it, if you take the sucrose and the fructose and you link them together, I don't know if I said this right, so I'm gonna start again. If you take the glucose and the fructose and you link them together to make the sucrose, it's a surprisingly hard problem. It is beta fructose, not alpha fructose. The fructose has to flip around 180 degrees from the way it's drawn in my data booklet, and then I can hook them together, and you have to know that. We're gonna do the same thing with the nitrogenous bases. Like, they're drawn there, but how do you orient them to show the hydrogen bonds? The drawing aspect for me is a little bit tough. And so I have the slides to kind of support when I can't draw the picture, but these slides are kind of garbage, so sorry. But the drawing is the skill here in a lot of ways. There's no reason these have to be the same fatty acid, it's just the easiest thing for me to draw. So here you can see there are 3 different fatty acids attached. The top one is stearic acid, the middle one is oleic acid. What's the bottom one? I believe it's palmitic acid. Where do you think I get palmitic acid? Palm oil. Where else would I find palm oil? There's usually quite a bit of it in Nutella, and so I like to think about the rainforest and the Nutella and decide which one I'm rooting for. But it was also in the Pop-Tart Ajay was eating, so it's everywhere. This is like a more adult approach at showing the cis versus trans. I don't think it's very good, but I think that we did this Coconuts are one of the few vegetable sources that's primarily saturated fat. Coconuts are one of the few vegetable sources that's primarily saturated fat. I think that's a good statement. Here you can see how things break down. I think probably the most important takeaway from this is just that when you take a source of oil, it's always a mixture of things. So it's not like when I take the olive oil that's in there and I try to do an experiment with it that it's all oleic acid, but it is definitely mostly oleic acid, but it's always going to be a mixture. You are more oleic acid than you would have thought. You've got apparently quite a bit of palm oil in you. Yum. Coconut oil over here is mostly saturated. There's a little bit of some unsaturated stuff. What? No, I think we're totally off the saturated fat is bad bandwagon. Trans fats are. I think there's pretty good evidence linking to trans fats to bad outcomes. Your body does not have a mechanism of processing this. So let's do some math. Isn't math fun? Oh, vectors are good. Skew. See, skew is two vectors that will never cross. Now, they're not parallel, which will also never cross. They're skew. I think I just totally made up the problem yesterday. So the iodine number is calculated as the number of grams of iodine that will react with 100 grams of a fat or oil or whatever. Moheb wants to know that the iodine number is a natural number, a number with no decimal points. It's a number, not a real. It's an integer, not a float.
Wow.
Yeah, that's more my language, right? The idea here is that I take iodine and a burette. Iodine's a solid, so I kind of dissolve it in some water. Does anyone know what color it's going to be? Brown. And down here I have an oil, and as my boy Brecken suggested, the oil that I've chosen is an unsaturated oil. Unsaturated oils have a functional group I'm pretty good at. They contain alkenes. The alkenol functional group, what class alkenes, functional group alkenol. And I know that they undergo a specific type of reaction, addition reactions. I even know that there are 4 addition reactions that I know something about. I know that I could add hydrogen, I could add water, I could add, something asymmetric like HI, and I could do what I'm actually supposed to be doing and add I2. If I take a rando alkene and I add H2 to it, what else might I need there to make the reaction occur? What reaction conditions? Nickel at 150 degrees. And the product would be an alkane. How about if I add water?
Sulfuric acid.
That is correct. I need concentrated sulfuric or phosphoric acid and heat. And I'm going to make an alcohol. HI is kind of cool because it's asymmetric, so I was thinking about adding it directly to propene. It doesn't actually take any like special conditions. It happens spontaneously at room temperature. But I have an asymmetric alkene and an asymmetric molecule that I'm adding across it, so I feel like I've got to think about Markovnikov. So remember, propene looks like this. It's asymmetric. Propene doesn't look like that. Propene looks like this. It's asymmetric. And so I was wondering how the HI would add. The H is going to add to the carbon with more H's, is Markovnikov's rule. Some of you also said that the carbocation intermediate would be stabilized on the secondary carbon via the positive inductive effect. But for our purposes today, you can see that what we're doing is we're just adding iodine, and you can see that those double bonds in the fatty acid are going to become saturated. But this thing here, it has a crazy name, but more importantly, it's going to look like oil to my eyes. And so I'm going to take this brown liquid, I'm going to pour it into the oil, I'm going to stir it, it's going to look like oil. I'm going to take this brown liquid, I'm going to add some more, and then one moment, something magical is going to happen. It's going to stay brown. So that is the end point of my titration, that iodine is left over. We still good? I'd like to calculate the iodine number. We can do it with this, I guess. That's too easy. It's all done for you. How about we do it for linolenic acid? Generally speaking, saturated fats shouldn't react. So animal fats have iodine number between 40 and like 100, and vegetable fats or polyunsaturated fats have between 100 and maybe 200. I don't know. I feel like that's coming out. I'm looking at my notes. It's the data booklet. So what is the chemical reaction that linolenic acid is going to undergo?
Addition.
It's going to undergo addition. Thanks, Quinn. How many molecules or moles, depending on how you like to think about the world, of iodine can this thing add? Or what is the stoichiometric ratio, say, between my fatty acid and my iodine? How do you know, Audrey? Because there are 3 double bonds, she knows that it's going to be able to add 3 I2s, and it's going to make the saturated, iodinated fat. I ain't drawing it. I don't care. Oh, I care. Written in a really, the old number applied by that. Sounded like someone was going down the hallway. Felt like it needed some adult supervision. It's left. You heard it. Thought I should see if anyone was there. How did I come up with that so efficiently, so fast, so amazingly well? Oh, because I went to the bathroom. That's where the problem was. What? Oh, you already just solved the problem just to help with the talking? Maybe let's just do it. So, if there's 17 carbons, how many hydrogens can that support? So if there are 17 carbons, what's the maxi number of hydrogens I can put on it? 36, and I've got to replace one of them with a coup, so 35. And so this sum had to be 35. I mean, everyone knew that there were going to be 6 of these. That's how you get the 29 without working too hard. The sum had to be 35. So just in case, because I think we're going to have to count up the hydrogens there, and I might come up with 2 ways. We'll see. Y'all suck. She's done. Okay. What are we going to do next? You don't know? No, you find a calculator. I was using twists all morning. The number of grams of iodine that will react with 100 grams of our fat. Oh my God, we're back to grams. I may feel like this is Sophia's day. So we're going to take 100 grams of our linolenic acid. But you guys gave me a stoichiometric ratio of 1 to 3. And if I need to use a stoichiometric ratio, what do I have to know about the linolenic acid? I need to know the molar mass because I need to know how many moles there are. So I need to figure out the molar mass of this. So I need to figure out its chemical formula. And I was trying to convince you that we knew it was this. And so maybe I could figure out its mass. And anyone who's playing along hopefully got 278.48. Did you get that? Your calculator's broken? So I would write it like this, I suppose. And then I'm going to say that there's 1 mole of linolenic acid that reacts with 3 moles of I2. And then I would say that every 1 mole of I2 weighs 126.94, maybe times 2 grams per mole. Sophia's braiding her hair, so I don't feel like she's really getting all the love out of this. She could. That's okay. And I got 273.49, 89945, in case anyone cares. This is just, I didn't know what the molar mass of iodine, the diatomic molecule was, so I knew I just by itself. So I was able to write that down in I2 it. I'm around that, and the iodine number is 273. No. I calculated how many grams reacted with 100 grams of the unsaturated oil. So our given was that we were going to have 100 grams of the oil. Her first, she raised her hand. Crazy tough. Yes, that is the definition. That's why I tried to write it there, because I didn't know that. Yeah. There's always a plus or minus couple. Okay, so this calculation, I would say, wasn't that hard. So, it's kind of interesting because to do that calculation, what I had to do is actually know what was in my unsaturated oil, but that's not the way it works. Like in a normal world, you have the opposite information. You have an oil you don't know anything about, and you add the iodine, and you're like, oh, now I know something about the oil. So let's see what happens when that goes out. Yes, what are all these words? There we go. A sample of vegetable oil, 5 grams, has reacted completely with 40 cubic centimeters of a 0.6 molar solution of iodine. What is the iodine number? And, dun, 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 many double bonds does it have? I think we can do those three calculations. I think we could get the moles of iodine that reacted. I think we could figure out the mass of iodine that reacted, and I think we should set up some sort of a ratio that says, yo, if like 5 grams of iodine reacted with 5 grams of vegetable oil, then I can predict if I had 100 grams of the oil, how many grams of iodine would have reacted, and that's the iodine number. So I think those are the 3 steps in my calculation. Moles of the iodine, mass of the iodine, and something to ratio to 100. Okay? Me too, because I took 40 by 60 and adjusted it. I multiplied that number by 2 by 126.94, and presumably I got about 6.1 grams. Is that still okay? And now I know a ratio that says 6.1 grams of iodine reacts with 5 grams of oil, as I don't know how much would react with 100 grams of oil, or others among you would just multiply that number by 20, and you get 122. And just use this ratio. We figured out not the iodine number, but the number of grams of iodine that would react with 5 grams, but the definition of iodine number is how much would react with 100 grams. So you can cross multiply or multiply by 20, whichever makes sense. Okay, and that leads us to the second part. We know the iodine number. Can we estimate the number of carbon-carbon bonds per molecule of the oil if its average molar mass is 865? 865 seems like a big number because like we only got 278 here, but I want you to appreciate just for a second that this is a fatty acid, and this here is an oil. This is a triglyceride. So this is going to be 3 fatty acids and a propane triol. So we expect it to be 3 times bigger, and it is. So we're rock star in that. So to me, to figure out the number of double bonds, it's this ratio that I'm really interested in. It's the ratio of the moles of iodine to the moles of the fat. Is it possible for me to figure out the moles of the fat? Because we already got the moles of the iodine. Yeah. So if I knew that the moles of the fat was 5 grams divided by 865 grams per mole, I don't know that number, sorry. Then I could take a ratio of this to that, and I get just over 4. And so my estimation is that there are about 4 double bonds in the whole triglyceride. And again, that makes sense to me because I could have 1 linolenic, 1 oleic, and 1 steric. by definition the grams that would react with 100 grams of oil. We knew how many grams reacted with 5. And so we either cross-multiplied or multiplied by 20. It's fascinating that all classes are the same. I hate to break it to you, but the other class could take no more at this point. And so we thought it might be nice to work on the homework that's due, today at midnight, or you can finish the protein assignment, or I gave you the lipid assignment and you are currently able to do both questions 1 and 3. So you officially have time to work, unless, you'd really like me to keep talking. Let's go, Amarachi. So the iodine number is the grams of iodine that will react with 100 grams of oil.
Is 100 just the standard?
Yes. So it's a definition, and I don't know that they always give it to you, so I looked it up, so it's not something we can So we didn't actually need to know how many moles of oil we had. We just needed to know that we were doing that experiment with 5 grams. We measured how many grams of iodine reacted.
So I reacted 5. Okay, so it's gonna be 5.
It reacted with what?
It reacted with so
Yes.
5 over 5. Yeah.
6.1 over 5.
Where's the 6.1?
That is, so you knew how many moles of iodine you had, so we multiplied by the molar mass of iodine. So we took 0.024 times 126.94 times 2. I2. And that's how many grams of iodine reacted. You okay?
Me?
Yes, you.
Oh, sorry.
You're sleepy on Marachi. I just want to make sure you're taking care of yourself.
Not really.
Sorry.
So you take the moles and then you divide it, and then you always have to do the time too because iodine is diatomic.
Yes, ma'am.
Okay. And then you get the
6.
6.1 grams of the iodine that reacted with it.
And so now I'm saying that 6 grams reacted with 5 grams. I don't know where this problem is. I'm sorry. Reacted with, nope.
It's here.
Right here. There it is.
5 grams, sorry. We can set up some sort of proportion.
Okay.
That's 6.1 grams reacted with 5, so how many would react with 100? Because again, that's the definition.
Oh, so 6.1 grams over 5 grams
Yes,
equals x over 100.
yes. And that's where we got 122, because it has to be a whole number.
Okay.
Yes. I see you, Mahab. She's just still chugging along.
Okay, thank you.
Okay.
So for this one, you said something
Oh,
like
this
we have
one
to,
right
this was the hard problem you were talking about.
Yeah, I
right?
thought it was hard.
Okay, so I just used the stuff in the data booklet, right?